Hey everybody, I'm Chili. Welcome back to 3D Fundamentals Tutorial 5. Today we're going to draw some triangles. Now you probably already know that 3D graphics boils down to basically just drawing a hell of a lot of triangles. But you ever wondered why triangles? Well, let me take you on a little thought journey. So far we've been working with wireframe rendering. But wireframe only makes it difficult to parse a complex scene. Like, look at this bullshit. You ain't gonna be understanding all of the detail in here. Now let's take a look at the same scene rendered with solid objects. You can't see anything behind the walls here, and so your brain has a much easier time making sense of the scene. So here, the 3D cue for our brain is occlusion. Things in front occlude or cover up things that are behind, and that's going to help our brain understand the scene. Now take a look at this. You got two cubes that were shittily drawn by yours truly, the white one and the red one. Now your brain ain't going to be able to figure out how this scene is working. There could be multiple scenarios here. You could have a very small red cube in front of a larger white cube, or you could have two cubes the same size, but the red cube is farther away. You can't tell which case it is, but if you had solid cubes, it would become clear, because if the white one, for example, was in front, you wouldn't even be able to see the red one at all. So solid rendering not only helps us to understand a scene by removing a lot of the complexity, but it also helps to establish distance and scale of objects in your scene. Now, when we render a solid object, all we have to really do is render the outside surface of the object. So that's how we store it in memory. We store it as a skin of the surface of the 3D object. Now there are many ways we can represent this skin mathematically in memory. We could represent it as a smooth mathematical curve, and this would be very nice, but it also happens to be very expensive. So that's not what we do. What we do instead is we approximate with polygons. And as you can see here, the more polygons you use, the closer your object is going to be to having, a perfect curve. And this is how we're going to represent our 3D solid models. We're going to implement them with a mesh of interlocking polygons like this. So now our problem of drawing a 3D object on the screen becomes the problem of drawing a bunch of 3D polygons to the screen. So how do we render a 3D polygon to a 2D screen? Well, look at a polygon in 3D space. You could represent that polygon as, the lines of the edges around the polygon, okay? So you've got points, and they're connected by lines, and that represents the outside contour of the polygon. But we already know how to draw 3D lines in 2D space. We just project the end points of the lines onto points on the screen space, and then we can draw between those. Now, to draw a filled-in polygon, all you're going to do is, instead of drawing those outside lines, you're going to fill in all the space that is contained by those lines. And that's all there is to it. Now, we call these corners of a polygon, we call these its vertices. And get used to that word, because you're going to be hearing it a fuck ton of a lot. So to draw a 3D polygon on the screen, you project its vertices onto screen space, and then you fill in all the space between the lines. Now, it can be hard to write an algorithm that can draw, any possible polygon, whatever you throw at it. Because they can have, nooks and crannies and shit. They can be all fucked up. But you notice one thing, and that thing is, any polygon can be broken down into simpler polygons, down to the simplest polygon, which is a triangle. And it's much easier to draw a triangle than it is to draw, this fucking thing, or this thing. Right. So, and this is a recurring theme in algorithm design, by the way. You take one complicated task and you break it down into solving a bunch of simpler ones. And that there is how you do. To render a solid 3D object, all you do is you project the vertices of the triangles onto screen space, and then you draw the 2D triangles. All right, let's take a look at how we draw a simple triangle here. So, you're going to start at this Y here and you're going to end at this Y. I mean, there's no point in considering any of these pixels or any of these pixels here because they're never going to be drawn, right? Your triangle's going to at least be between these coordinates here in the Y. Now on this triangle here, we have these nice left and right edges, and these are lines, right? They have equations. We can find points on them. So if we want to draw the triangle, we can start at this Y, and we can get, at this Y position, we can get the X of this line and the X of this line, and then we draw between those two X's on this Y, this horizontal Y plane. Then you move down to the next Y. You calculate your start X and your end X based on this Y, and you draw through. Then you go to the next one, you start, your end, and you draw all the pixels between. Very fast operation, and this is why it's called Scanline Rasterization. You're just scanning across these lines. Now, we call this kind of triangle a flat bottom triangle, and as you all know, they are what make the rockin' world go round. You can also have a triangle like this, and it's basically the same idea. You still got your left side, you still got your right side. You're going to start at this Y, you're going to scan between the two lines, calculating your start X and your end X for every Y scan line. And we call this a flat top triangle. Arsenio Hall. Now, unfortunately, very few of our triangles are going to be flat bottom or flat top. Most triangles are going to be like this, a general triangle. And this one has a problem because if we start scanning from here to here, about halfway through, our line here changes direction. So we have a different equation to solve for the start X now. And the way we solve this problem is, again, we break the problem down into smaller sub-problems. So we know how to draw a flat bottom and a flat top. So what we can do is we can draw a line here from this vertex to here. And the intersection of this line, this horizontal line drawn from this vertex and this right side line, the intersection point is going to be a new vertex for us, and we're going to split the triangle into two triangles. And now these triangles are flat bottom and flat top, which we know how to draw easy. So for a general triangle, you split it up into flat bottom and flat top. And we can find this division point with a little bit of math. It's not too hard, just some linear equation. So in general, you've got two cases for your triangle. You've got a major left triangle where the long side is on the left, and a major right where the long side is on the right. And those can be split up into flat bottom and flat top. And sometimes you'll just have a natural flat bottom or a flat top, so you can just, do that directly. All right, there's one final detail that we have to discuss before we can dive into the code, and that's how to determine when we set a pixel. You might think, well, anytime if any part of the pixel is inside of the triangle, then we set that pixel. So we set this pixel, we set this pixel, we set this one, we set this one because there's a little bit in there, and this one, and you get the goddamn idea. You don't need me to fill this whole fucking thing in. And that's one way of handling it. But here's the thing. Your geometry is going to be made up of a mesh of interlocking triangles. And so, for example, this triangle here is going to try to, set pixels like here and here. It's going to try to set this pixel. It's going to try to set this one and this one as well. But this triangle here is also going to want to set those pixels. So who fucking gets to set them? Do they both draw, and the last one who draws wins basically? Then they're fighting over the color. You can have like pixel flickering depending on the order of drawing if it changes from frame to frame, and it's just wasteful having to fill that memory multiple times for different triangles. It's kind of dumb, right? And you could say, okay, well then all I'm going to do is I'm only going to fill the pixels that are completely inside of the triangle. But that's even worse, right? Because now you got these huge gaps between your triangles. You're supposed to have a solid mesh, but instead you've got all these gaps between your goddamn triangles. That's bullshit, right? So what we need is a set of fill rules or rasterization rules that will make it so that all pixels in a mesh of non-overlapping triangles are only drawn once, but with no gaps between. And what we're going to be doing is we're going to be using the rasterization rules for Direct 3D 10 and 11. I think it's the same for 12 as well. First off, let's review the coordinate system for Direct 3D 10 and 11. So the way we treat our pixels in screen space in terms of floating points is as following. So the pixel 0, 0, the integer pixel 0, 0, it occupies the space in float between 0 and 1, including 0 but not including 1. So from 0 up to but not including 1 in the x and the y. And that's pixel 0, 0 in integers. And the center of that pixel is at 0.5, 0.5. This is actually different than Direct 3D 9. They had the centers of their pixels at 0, 0, for example. That was the center of the pixel 0, 0 was at 0, 0. So the top left-hand corner of the pixel was at negative 0.5, negative 0.5. It's a fucked up system. Don't even get me started. This one's a lot nicer. So, with that understood, let's take a look at our rasterization rules. Now the rule that we're using, it's called the top left-hand rule. Now the first part of the top left rule, and this is pretty much the same for any rasterization rule, is if the center of the pixel is inside of the triangle, you draw that pixel, no matter what. But if the center of the pixel lies on one of the edges of the triangle, then it's not so clear. Like you got two triangles here. The center of these pixels is exactly between these two triangles. So you need some kind of a tiebreaker rule to determine which triangle is going to get to set those pixels. And the top left-hand rule says that if a pixel center is defined to lie inside of a triangle, if it lies on the top edge or the left edge of a triangle. So for this one here, you see that this triangle, the bottom triangle, the pixels here are lying on its top edge. So this triangle gets to draw the pixels. This one is shit out of luck. Here, we see that there's a tiebreaker situation here, and it's on the left edge of this triangle. So this triangle gets to set these pixels, and this triangle is, again, shit out of luck. Now, you might look at some of these cases here. They give you a lot of example cases, and these make it easy to understand the rasterization rule. But you might look at some of these. You might look at this one and say, well, this pixel looks like it's on a top edge, but it's not getting drawn. But if you look at the definition for a top edge, is an edge that is exactly horizontal and above the other edges. This one is above the other edges, but it is not exactly horizontal. So this does not correspond to a top edge, and therefore this pixel doesn't get drawn. This pixel gets drawn because it's on a left edge, which is an edge that's not exactly horizontal, but it's on the left side of the triangle. Triangle can only have one or two left edges. And you see, with these fill rules, sometimes triangles don't get drawn at all. Look at this triangle. No center falls on or within the triangle, so it'll never get drawn here. This triangle, it falls on some centers, but the centers that it falls on don't follow the top left rule, so this triangle here also doesn't get drawn. And the top left rule here, that's what we're going to live by and die by as we rasterize our triangles. All right, let's take a look at the code now. I've added a function, draw triangle. It takes 3 vectors. These are the vertices of the triangle that we want to draw, and it takes a color, the color that we want to fill the triangle with, obviously. Now, this one is going to dispatch calls to draw flat top triangle and draw flat bottom. So draw triangle is going to figure out what kind of triangle we have, and it's going to split it up into flat top and flat bottom if necessary, and then call these guys. So these guys are private. They're not part of the external interface. People just call draw triangle, and it does all of the work for us. It figures out all the shit. So let's first take a look at draw triangle. Now, I'm passing in by constant reference because I like that syntax, but we actually want pointers because we want to be able to switch which pointer is pointing to which vector, because we're going to sort these fuckers. We want them to be sorted from V0 is at the top and V2 is at the bottom. So we create these pointers, and then we swap to sort the vertices so that PV0 will be the one at the top and PV2 will be the one at the bottom. Now, after we sorted these fuckers, if V0 and V1 have the exact same y value, that means that it must be a flat top triangle, right? Like this situation here, the y's are the same, we got flat top triangle on our hands, and all we're going to do there is just, first off, we're going to check to make sure in a flat top triangle, we want to sort it so that V0 is on the left. So we swap if V0 is on the right, and then we just call draw flat top triangle. And it's the same deal for flat bottom. We test to see if V1 is the same as V2 in the y coordinate. If so, we sort them so that V1 is on the left, and then we draw a flat bottom triangle. Otherwise, we have a general triangle. And in that case, what we're going to do is we're going to calculate the splitting vertex, and then we're going to check to see if we're major right or major left and call flat bottom and flat top accordingly. Now, the way we're going to solve for this splitting vertex is we're going to use linear interpolation between V0 and V2, right? This vertex is going to be somewhere between V0 and V2. So what we do is we look at this distance here compared to this distance here, and this is going to determine how much closer this point is to V0 than it is to V2. So this ratio here is going to give us what we call our alpha. I mean, it's a prerequisite for this course that you understand linear interpolation, but let's just do a quick little overview here. So the y difference here, the difference in the y here is going to be, so V1y minus V0y. That's this distance here. And the ratio of that over V2y minus V0y will give us the ratio of this distance between this distance, right? And we're going to call that ratio alpha. So if alpha is 0, that means that V1 is basically at this starting point is basically at V0. Whereas if alpha is 1, that means that this cutting point is really close to V2. So all we've got to do now is we basically take the weighted sum of alpha and the complement of alpha times V0 and V2. It looks like this. So if the splitting vertex is VI, then VI is equal to 1 minus alpha times V0 plus alpha times V2. So to take a simple case, if our splitting point were right in the middle of this y and this y, then what we'd have is we'd have VI is equal to 1 minus 0.5 V0 plus 0.5 V2, which is just VI, there's an equal here. That just means VI is equal to V0 plus V2 over 2, or just the average. So if it's right in the middle, you're just taking the average of these two vectors. On the other hand, if the splitting point were right at the top here, you'd be VI is equal to 1 minus 0 V0 plus 0 V2, which would just be equal to V0. So that would just be V0. And the other way, if you were alpha of 1, you would just be V2. And any number in between, you get one of these vector points along this line here, in between these two vertices. And we can rewrite this expression for the splitting vertex. We can multiply out this expression here, and then factor out alpha, factor out actually negative alpha. And we get this expression here, V0 plus V2 minus V0 times alpha. And that, my friends, is what we got right here. So alpha is just V1y minus V0y over V2y minus V0y. And then you got V0 plus V2 minus V0 times alpha. And there you go, you get your splitting vertex. Now, we can use a splitting vertex to determine whether we have a major right or a major left triangle, right? So if the x of the splitting vertex is greater than the x of V1, then we're major right. If it's less, then we're major left. And this is important because our flat bottom and flat top triangle drawing routines expect the vertices in a certain order. So for a major right, you're going to have, for example, for the flat top, you're going to have V1, VI, and then V2. But for this one, for major left, you're going to have VI, V1, and then V2. So you've got to detect which case you have and pass in your vertices in the proper order. And that's what we're doing here. Notice that the orders of V1 and VI depend on whether it's flat or whether it's major right or major left. Orders get flipped around. And now we get to the juicy rasterization. So we got draw flat top triangle here. And the first thing we're going to do is we're going to calculate the slopes of our left and right lines. So that's this guy here and this guy here. And one thing to note about what I'm doing here is I'm calculating the slope as the run over the rise, which is actually probably inverse of what you're used to from math class. And there's a good reason for that. For our triangles here, the left and the right side, it's possible to have a slope going straight up. And if we did delta y over delta x, the slope would be infinity, right? This is infinite rise over run. So instead of doing rise over run, we do run over rise, and we avoid getting an infinity slope, because we're not going to have any perfectly horizontal lines for our left and our right triangle edges. They're always going to be either vertical or slanted. Then we calculate the start and the end scan lines. That's the start and the end y coordinates in integer space. And we're doing this calculation using the top left rule. And the way we implement the top left rule is with the ceiling function and by subtracting by 0.5. And doing this will give us the top left rule for the y coordinates. So how does that work? We'll take a look at this triangle we got right here. Assume that all the edges lie on pixel centers. So according to our rasterization rules, we would expect this pixel to be filled, this pixel to be filled, and this pixel to be filled. We can verify this if we look at the diagram for the rasterization rules. This triangle is exactly our triangle. And it should be this one, and this one. Not any of these. This one here is being filled by the bottom triangle. So that's what we expect to happen. Now, let's take a look at what happens to these y coordinates when they get pumped through our algorithm. So we're taking, where is it? Stupid thing. Here we go. So we're taking V0, we're subtracting 0.5, and then we're taking the ceiling of that. Now the ceiling means that, for example, if the value is 0.1, round it up to 1. If it's 0, keep it at 0. So the ceiling of 0.5 minus 0.5 is the ceiling of 0, which is 0. So we should start at y coordinate 0, which is correct. We want to start at this scan line here. Now our end is going to be a little different. No, I lied. It's actually the same operation. And what that means is that our end is going to be, well, this is 0.5, 1.5, so this is 2.5 minus 0.5 is equal to 2. So we end at 2, but we're not filling this in, but that's okay, because if you look at our for loop, you'll see our for loop goes up to the end, but not including. So what we're going to do is we're going to scan this one, we're going to scan this one, and then we're going to stop here. This is the stop scan line. So go from 0 up to, but not including 2. And that's what we're doing here. We're only drawing this scan line and this scan line. Now, as one more quick example, if we make our triangle extending this vertex down a little bit, we're going to start at the same place, start at 0. But where's our end going to be? Well, let's say this vertex, its y coordinate is 3.4. So 3.4 minus 5 is 2.9. The ceiling of 2.9 is 3. So we're going to end at scan line 3, meaning we'll draw scan line 0, 1, and 2. And the fill for this one is going to look something like this. Notice now that this pixel center is within the triangle, it's not on the edge. So now this pixel is going to get filled. And because we extended down here, this pixel will also get filled because it's now on the left side, it's not on the bottom corner. And then we're going to start our loop in the scan lines in the y coordinates. And for each scan line, we're going to calculate the starting x and the ending x in floating point numbers. And how we do that is, all right, so say we're trying to calculate this px0, which is the start x, and px1, which is the end x. So we have the x coordinates of the top vertices, right? And we have the y coordinate of the top vertices. Now we know the slope. which is the change in x for a change in y. So then we just got to calculate how much of a change in y are we moving from the top vertex to our current scanline. And that is just going to be our current integer scanline plus 0.5, because we want to be at the middle of that pixel, minus v0y, which is the y coordinate of our top vertices. So this distance here is how much we're moving in the y. We multiply that by the slope to get how much we move in the x for that much of a move in the y, and then we add that to our starting x, which is v0x. And when we add that, we get our x for px0. And you do the same thing for this one. Multiply dy by the slope, you get your change in x. That gives you this x here. Now you know your start x and your end x in floating point. Then when you're converting that to integer, you do the same thing that you did for the y's, which is you subtract 0.5 and you take the ceiling. And that will give you, again, the top left rule. So this is the top part of the top left rule. This is the left part of the top left rule. And this x end is going to be the end condition of the for loop, but because we're doing a less than for loop, it's not actually going to draw this scan line. It's only going to draw up to this scan line, and then it's going to stop. And then it's easy. Bob's your uncle. You start your x from x start. You run it until x end. You increment x, and you put pixel x, y, c for color. And there you go. Bob's your uncle. You're going to be drawing fucking triangles all day long. And flat bottom triangle is basically just the same garbage. All right, now we want to draw some garbagey triangles. So what we're going to do is we're going to want to render our cube with triangles instead of with lines. So what we're going to do is, first thing first, we're going to create a new data type called index triangle list. It's actually going to be exactly the same as an index line list. I just want to give it a different data type, to keep things nice and separate. So you got a vector of vec3 for your vertices and a vector of size t for your indexes. And what you're going to have is, in your indices, you're going to have 3 indices for every triangle. And those are going to index into your vertices vector. Now in cube.h, you're going to add index triangle list. And the cube is, the vertices don't change. It's the same cube. But you're going to add a new function, getTriangles, and that is going to return a copy of the vertices plus indexes required to, have triangles drawn for all of the sides of your cube. So this is our cube with the vertex indices labeled, and you can see here 0, 2, 1, 0, 2, 1. That draws this triangle here. And 2, 3, 1, 2, 3, 1. That draws this triangle here. So this line corresponds to the front face of our cube, and likewise all these other lines correspond to the other 5 faces of our cube. And in game.cpp, it's mostly the same story, except now instead of getting lines, you're going to get triangles, and that will return an indexed triangle list. You're going to generate your rotation matrix. You're going to go through each vertex in your geometry. You're going to rotate those vertices. You're going to offset them in the Z. You're going to transform them to screen space. Now, when it comes time to draw, you're going to get an iterator to the beginning of the indices and to the end of the indices, and you're just going to iterate through, advancing by 3 every time. And then for every time you advance, you're going to draw a triangle with these 3 indexed vertices. You're going to dereference the iterator. That'll give you an index. You're going to index into your vertices. That's vertex 1. You're going to index into the next iterator to get vertex 2, and then the next one to get vertex 3. And I'm just going to draw that with white. And if you do that, you get something like this. And indeed, it's a solid cube. But there's a problem. We're drawing all these goddamn triangles with the same color. So we have no way of differentiating edges or different faces because everything's goddamn white or whatever color you pick. So this is great if you want to draw a silhouette, but it's not so great if you want to understand the 3D structure of an object, because you can really only understand its outside silhouette. by this deal. So what does a guy do? Well, what I decided to do is create an array of different colors, and when we're drawing our triangles, we're also going to index into that array of colors. So this value here is going to increase by 1. So first triangle is going to be 0, next triangle is going to be 1, 2, 3, etc., all the way to 12. 6 sides on a cube, 2 triangles per side. That's 12. And if we do that, we get something quite interesting indeed. This is an interesting situation you got here. So my question to you for the end of this video is what the fuck do you think is happening here? And how the fuck do you propose that we solve it? I'm not going to tell you. That's for next time. But yeah, the topic of next video is going to be what the fuck is this and how do we fix it? But until then, I hope you enjoyed the video. If you did, please click the like button. It helps a lot. And I will see you soon with some more 3D fundamentals.